Good evening. My name is Boris Kulmai, and I'm a professor here at the School of Physics in the University of Sydney. Before proceeding, I would like to acknowledge and pay respect to the traditional owners of the land on which we meet, the Gadigal people of the Eora Nation. It is upon their ancestral lands that the University of Sydney is built. As we share our knowledge and discoveries within this university, may we also pay respect to the wisdom embedded forever within the Aboriginal custodianship of country. Tonight, we have the privilege of hosting Professor Shanhui from Stanford University for a fascinating public lecture we'll come to shortly. This lecture was made possible by a generous donation to commemorate Dr. Peter Domachuk, this handsome chap. Peter was a colleague and friend, starting as an undergrad physics student at this university. After completing his undergraduate degree, he joined the research group led by Professor Ben Eggleton as a PhD student, and then he took a position in Boston in the US in the emerging field of biophotonics. There, he was part of a several groundbreaking demonstration in silk photonics, bringing implantable, biocompatible optical devices, components closer to reality. Silk photonics has actually now also been used for radiative cooling, a topic that Professor Fan will tell us about more shortly. In 2009, he returned to the University of Sydney School of Physics on a prestigious research fellowship. He established a new research program and a new laboratory and built linkages around Australia. It was during this time where his research leadership was really taking off that he tragically passed away on New Year's Eve 2012, aged only 33. Quoting Professor Eggleton, his PhD supervisor, Peter was a unique character, highly intelligent, with a dynamic and energetic personality. He was equally at home discussing the philosophy of science or being a bouncer at Sydney's toughest nightclubs. Behind his brash personality, though, Peter was a sweet and caring young man with a love of life. And in his friend Steve Manner's words, Pete, as we say with a smirk, sat somewhere between mad creative genius with a thread of belligerence. He had a talent for science, for investigation, and for storytelling, always able to communicate complex ideas in a digestible form. And those traits and the imagination and knowledge that came with them went beyond the lab and into other interests in music, food, and the world at large. Peter certainly was a bon vivant. He loved good food and wine, and it is in that spirit that we invite you to join us for a cocktail party after the lecture. Now then, to the Peter Domachuk lecture, made possible by the generous donation by Peter's family. This lecture series is hosted by the University of Sydney, the Faculty of Science, and the School of Physics. They commemorate Peter's life and his contribution to the university. And these lectures support the sharing of information from world-leading optical physicists with students, researchers, and the general public. It is an activity of IPOS, the Institute of Photonics and Optical Science, the umbrella organization of all researchers working in optics and photonics at the university, also beyond the School of Physics. Tonight, we are delighted and honored to welcome Professor Shanhui from Stanford University. Professor Fan is a Joseph and Honmai Goodman Professor of the School of Engineering at Stanford University. He's received his PhD in 1997 in theoretical condensed matter physics from MIT. Professor Fan is a globally renowned physicist whose pioneering research in nanophotonics has transformed how we think about light, energy, and information technologies. His discoveries have inspired thousands of researchers worldwide, including myself. He has published over 700 refereed journal articles, given over 400 plenary keynote invited talks. I can't believe it. It's a lot, well done, and holds over 80 US patents. Professor Fan is undoubtedly one of the smartest people I know, and it is befitting he has received so many awards, including the R.W. Wood Prize from Optica, the Simmons Investigator in Physics Award, and a Vannevar Bush Faculty Fellowship. He is a member of both the US National Academy of Engineering and the US National Academy of Science, and a fellow of APS, OSA, SPIE, IEEE, etc. Please join me in welcoming Professor Fan to the stage.
Oh, sorry. Oh, yeah, that would be good. Yeah. Okay, that works. Well, thank you, Boris. And also, it's really a great honor to be invited here to give this lecture. Today, I would like to talk about some of the basic control of thermal radiation and also the implication of that in energy technology, in particular for passive radiative cooling. So here's a brief outline of my talk. I thought I would start, since this is a public lecture, to give a very brief overview of thermal radiation. Thermal radiation is a ubiquitous aspect of nature, and you see that every day. So here's one picture. This is the thermal radiation from the sun at a temperature of approximately 6,000 Kelvin, and it looks white, and that's the maybe one of the defining characteristics of thermal radiation at such high temperature. More down to earth, here's another picture that you probably are also quite familiar with, and this is a burning oven, and this has a temperature of about 800 Kelvin. And what you see here is that it looks red, and also if you stand in front of the oven, you get heat up. And what heats you up is actually the infrared part of the thermal radiation from the burning oven. Now finally, here's another example, maybe slightly less familiar, but nevertheless pertains to everybody sitting here. You have a temperature somewhere close to 300 Kelvin. Now, you don't glow unlike the stars and the fires. So if we turn off the light here, you're not going to see anybody. However, you do emit some radiation, and this can be seen if you actually take a look at an infrared camera image. So all these observational facts about thermal radiation is explained in this Planck's law of blackbody radiation, which gives you a plot of the spectral flux density as a function of wavelengths. So for example, the blue curve here is the blackbody radiation spectrum of a 6,000 Kelvin blackbody. So this is the emission of the sun, and it peaks in the visible wavelength range. And consequently, it sees white because all these visible colors are very well represented in the thermal radiation spectrum. Now, if you go to 800 Kelvin, which is the burning oven, in this case, you can see that the tail of the thermal radiation actually enters into the visible light spectrum. And it enters from the long wavelength side. So consequently, you see it as reddish when you look at the fire in the burning oven. Most of the emission in this case, however, is not in the visible spectrum, but rather in the infrared part, and that's the so-called heat ray that you feel when you are standing in front of the oven. Now finally, about ourselves, in this case, the temperature is low, and the emission is very far away from the visible spectrum. In this case, you don't see any of us glow in the visible wavelength range, but nevertheless, the infrared camera, which can pick up the longer wavelength radiation, can still see you. So in other words, the Planck's law of blackbody radiation perfectly accounted for much of what we observe empirically about thermal radiation. So this is figured out by Planck. Now, this is, of course, standard textbook stuff. But it is interesting to observe that this is, in fact, one of the major theoretical puzzles in the beginning of 20th century. And it took a lot of leading scientists at the time to figure out that the law of blackbody radiation really should look like this. And many of the leading scientists at the time, including Planck, Albert Einstein, and many others, actually contributed to the establishment of this understanding of thermal radiation. And it also is the beginning of quantum mechanics, the Planck's constant, which is one of the most important constants that characterize thermal radiation, characterize quantum mechanics, actually first made its appearance in this Planck's law of thermal black body radiation. So it really was a great achievement, in fact, theoretical achievement, to actually figure out this law that account for so much of our empirical observation about thermal radiation, and also has a deep connection to the beginning of quantum mechanics. So perhaps to summarize this very historical comment about thermal radiation, it is useful again to reiterate that is, it is a ubiquitous aspect of nature. Everything that you see, in fact, emits thermal radiation from the sun to the light bulb to your human bodies and so on. Now, this is at least a 100-year-old subject. But in the past 20 years or so, there is a very substantial new development about the ability to control the thermal radiation. So if you recall what we have mentioned about these black body thermal emitter, and perhaps one of the most well-known example is the tungsten light bulb. And if you heat up a piece of tungsten to high temperature, it emits visible light. Now, you can see that it actually looks white, and therefore it emits broad band of thermal radiation. You can see it from pretty much anywhere in the room, and so it's wide-angled. And also, there are quite a few important other constraints. For example, the total emitted power is constrained by what's called the Stefan-Boltzmann law, or the black body law, and the absorption and emission are related by the Kirchhoff law. And so, in the past 20 years or so, what people come to realize is that every single aspect of the standard black body radiator, in fact, can be altered if you look at modern photonic structures. And so consequently, that gives rise to a completely new class of thermal radiator that doesn't behave like a standard black body thermal radiator. So I just want to give you also a few examples. So this is one of the pioneering work by John Jack Griffith. The experiment that he did is to take a piece of silicon carbide and then put a grating on that. So he basically etched groups, a periodic array of groups, into the silicon carbide. When he does that, it turned out that the emission, the thermal emission of this structure, become highly angular. If you heat it up, it emits only along particular directions. And there's also possibility to create narrow band thermal radiation. In other words, thermal radiator that doesn't look white, but rather emit only near a single color. And here is a work from Willie Padilla's group. He looked at these gold micro antenna. So this is a cross made of gold with a size on the order of a few microns. And what he sees experimentally is that these gold antenna, the thermal emission is highly narrow-banded. So in a conventional thermal radiator, there is an upper bound of how much thermal radiation that you can get, and that upper bound is dependent upon the area of the structure. And it turned out that with photonic engineering, you can also overcome it. This is one of our own experiments carried out by Professor Zhongfu Yu, now a professor at University of Wisconsin. What he showed was that if you take just a black dot of carbon, which behave as a, oops, I was hoping to point, maybe not, a black dot of carbon, which behave as a standard radiator. Now, if you just put on top of it a semi-transparent dome, you will actually get the total emitted power that's much larger compared with that black body. So finally, one of the very important property of thermal radiator is something called the Kirchhoff law. And that says the absorptivity and the emissivity must be balanced in an angle by angle and frequency by frequency way. And as it turned out, this again can be broken. This is some of the theoretical prediction that we have done looking at a semiconductor material under a magnetic field. Again, in this case, with the presence of magnetic field, you see this absorptivity and emissivity at the same angle and a frequency that split from one another. And this has been quite recently demonstrated experimentally in a collaboration with Harry Atwater's group. So to summarize this very quick overview of the study of thermal radiation for over the past 100 years or so, perhaps it is useful to say that it is actually a very important aspect of nature, that you see that in everyday life. On the other hand, the use of modern technology, especially the ability to create structures at small scale, at nano and micrometer scale, has led to completely new properties associated with the thermal radiator. Now, as is typical, anytime that you gain control over a particular aspect of nature, that create new engineering and technological possibilities. So here, I would just like to highlight some of those capabilities by focusing on a set of works that we have carried out in the past decade or so related to radiative cooling. So the basic premise of radiative cooling is to try to benefit from the coldness of the universe. The universe is known to be very cold, has a nominal temperature of about 3 Kelvin. Now, from a basic thermodynamic point of view, something that's that cold is actually very useful. In the energy conversion, there's what's called the Carnot efficiency limit, which says that to get high efficiency conversion from heat to work, you would need to have a high temperature heat source. For example, the sun is very good at it. But you also would like to have a low temperature heat sink. Now, the vast majority of the technology today use the Earth itself as a heat sink at 300 Kelvin. And life would be better if you instead use the 3 Kelvin background of the universe as a heat sink. Now, the thermal radiation comes into this picture because we do have radiative access to the outer space. So I have mentioned that a 300 Kelvin black body spectrum, as indicated by the red curve here, has its peak in the mid-infrared wavelength range. And this is on the wavelength scale of about 10 micron. And this wavelengths happen to coincide with the transparency window of the atmosphere. In the wavelength range from 8 to 13 micron, the atmosphere is largely transparent. So consequently, any 300 Kelvin black body or any thermal emitter, if you that include every one of us, if you go out of this room, if the sky is clear, you will actually be radiating heat out through the atmosphere to the outer space. And that corresponds to a fundamental cooling mechanism because you are getting the heat out from your body to the outer space. As a result, so this kind of cooling actually can be seen experimentally, and this has been known for many decades, and it's called nighttime radiated cooling. So at night, if you take a black emitter and you surround it with insulating material, a styrofoam would have done it, and you allow the emitter to face the sky, then it's actually a very straightforward experiment to show that you can get the emitter to get to a temperature of about 10 to 15 degrees Celsius below the ambient temperature. And this is a technology that actually has found some use. For example, one of the buildings at Stanford would have used this technology to get cold water at night. But it's a technology that has not been extensively used. And the reason is a very simple one, that usually daytime is hotter, so you need cooling more during the day. Now, during the daytime, in spite of all I have told you about the fact that you'll be miraculously radiating heat to the outer space if you just get out of this room, during daytime, if you actually step out of this room, you won't get any cooler, usually. And that's because the sun is heating you up. So from that comes this idea in thinking about daytime radiated cooling by photonic engineering. So the idea is to try to design a structure to shape the spectrum, the response spectrum. So you would like a structure that doesn't get heated up by the sun. So for example, you want it to be a very good mirror in the visible and near infrared part of the wavelength range. On the other hand, you would like this to be highly emissive in the wavelength range of 8 to 13 micron. So together with Eden Raffaelli and Ashwat Raman, we wrote this theoretical paper. We designed a photonic structure that has a emissivity spectrum that looks like schematically like what I show. And we did some calculation to show that if you actually build a structure like this, then you should be able to get sub-freezing temperature under the sun. In other words, at a temperature of about 30 degrees Celsius, if you build a structure and done it right, you are going to see a temperature below 0 degrees Celsius passively. And the cooling power of this thing exceeds 100 watt per meter square. So that was a theory that we did. Of course, when we published a theory like this, it looked like yet another strange-looking theoretical prediction. But we actually took our theory fairly seriously, and we spent quite a bit of time thinking about whether we can simplify this design to actually give us an experimental demonstration. So we eventually construct a structure on an 8-inch silicon wafer. And the picture here on the left shows Ashwat Raman, who is now a professor at the University of California in Los Angeles, and Lin Xiaozhu, who is now a professor at Penn State University. And what we're staring at is a mirror made on an 8-inch wafer. And this mirror is made out of depositing a thin film of silver on top of silicon, and that becomes the primary reflecting thing. And then on top of silver, we put multi-layer of hafnium oxide and silicon dioxide. So in this system, the thermal radiation primarily comes from silicon dioxide. And so the silicon atom and the oxygen atom at room temperature oscillate against each other, and that emits thermal radiation. And the hafnium oxide was put in to further shape the thermal emission spectrum. So in the long wavelength side, in the wavelength range of 8 to 13 micron, one sees a emissivity peak. On the other hand, in the solar wavelength range, it behaves as a very good mirror, as we show in this image. We then bring the sample to the roof of our electrical engineering building. Remarkably, we actually had a very nice flat roof for this kind of experiment. And on the right are some of the experimental data. So the black curve is the ambient air temperature, and the blue curve is the temperature of the radiated cooler that we have constructed. And this is under a solar irradiance, the amount of sunlight that's around noontime that's hitting the sample at about 900 watt per meter square. So in spite of this solar irradiance, this structure actually has a temperature that's about 5 degrees Celsius below the ambient air temperature. And this is done entirely passively without any energy input. So there are actually a few things that are quite amusing about this experiment. You can see in the beginning of the data, the temperature starts at ambient air temperature. So when we bring the sample to the roof, initially we cover the sample so that it doesn't see the sky and the air, doesn't see the sky and the sun, and so therefore its temperature is at the ambient air temperature. Then we take off the cover. Now, usually if you have an object and you take off the cover, it sees the sun that you will heat up. This thing actually does the opposite. Actually, when you take off the cover, the temperature starts to fall. And that's coming from the radiative cooling effect. So once you have this thing that has a temperature below ambient, you can put a heat load on it. You can heat it up. And you can ask how much heat can you actually put into the structure in order to bring it back to the ambient air temperature. And this number in our initial experiment turned out to be about 40 watt per meter square. So you actually have to put this amount of heat into it in order to drive the temperature back in the ambient. And that becomes how much cooling that you can actually generate with these structures. A modern experiment beyond has easily demonstrated 100 watt per meter square of cooling power. So since then, there have been many experiments on these daytime radiated cooler, and I just want to highlight a few of those that we're involved in. This is a collaboration with Professor Jia Zhu's group. What he did is he figured out one of the ways to make a large-scale fabrication of these radiated cooler. He looked at these polymer films. These polymer films has fibers that are, the chemical structure is such that it emit radiation. On the other hand, it also has a microstructure on the wavelengths of light, and therefore it strongly reflects light. And that fulfills both of these requirements of a radiated cooler. And furthermore, he has developed these roll-to-roll electrode spinning process that allow him to produce these kind of radiated cooler on a continuum basis. And many different materials can be made into sub-ambient radiated cooler. And this is one of the work, I guess, Boris just hinted at. That's also connected to the silk photonic work that he mentioned. In this case, we configure silk into a sub-ambient radiated cooler. So silk is a natural fiber that's actually quite reflecting, but it turned out that it's not reflected enough for radiated cooling purposes. So in this work, Zhu Jia's group introduced zinc oxide nanoparticle attached to the silk to enhance the ultraviolet part of the reflectivity, and that's enough to get the silk to reach sub-ambient temperature under the sun, again, passively. So in a way, this shows that you can, in some sense, wear your own air conditioner. So this is a very active area of research on thinking about using textile for these thermal management purposes. And I also like to highlight Dr. Alex Song's group here, who are doing also very exciting work along this direction. There are also interesting possibilities of combining radiated cooler with other cooling technology. So here's a work where we combine that, radiated cooling with evaporative cooling. So both are passive cooling technology that have complementary strength and weakness. Radiated cooling does not require water. This is just the thing goes out. But it doesn't work that, but it requires a clear sky. It doesn't actually work that well if the sky is cloudy. Evaporative cooling, on the other hand, does work even when the sky is cloudy, but it takes water. So one of the ideas is to combine them. So in this combination, we have the radiated cooler put on top of a hydrogel that acts as a water storage compartment. So at nighttime, the radiated cooler will function, and as a result, the water will condense on the radiated cooler, and those can be harvested and stored into the hydrogel. At daytime, the radiated cooler will cool, but also the water from the hydrogel can evaporate. So the daytime, you can combine radiated cooling and evaporative cooling. In doing so, one can alleviate some of the difficulty about evaporative cooling that require water by directly harvesting water from the sky. But in the meantime, combining these two passive cooling mechanisms to ensure that it has a larger cooling power and also a wider range of operation. So one of the potential application of radiative cooling is in building air conditioning. Now, as I've shown you, these experiments are done on the rooftop. For many modern buildings like this one, is constructed to be well insulated. The result is that if you create cooling on top of the roof, you still need to be able to deliver that cooling into the building. And so in this experiment, we construct these cooling panel with circulating water loop underneath it so that you can cool the water temperature to be about 2 to 3 degrees Celsius below the ambient air temperature. This water, cooled water, can then be used in a water-based cooling tower in a standard air conditioning system, and the reduced water temperature of a few degrees translate into 10 to 15% improvement in the system efficiency. 15% of US power consumption goes to air conditioning. So a way to systematically improve air conditioning system efficiency, therefore, can be potentially important commercially. So Eli Goldstein, a postdoc of mine, and Ashwath Raman and myself started this company called SkyCool System, which tries to deploy these daytime radiative cooling panel for air conditioning of buildings. So here's one example of these deployment of the system built by the SkyCool System on a supermarket roof in California. And you can see the cooling panel here, as well as the circulating water loop underneath it. You can see the pipes. And this leads to substantial annual electricity saving. And we now have a deployment of this in a number of supermarkets as well as data centers around California. So I've talked a little bit about the practical side of the radiated cooling. It would be interesting to ask from a more fundamental side, how cold can you really do with this technology? Now, this is a technology that's in essence trying to establish thermal equilibrium with the outer space. And the outer space is 3 Kelvin. So consequently, if the atmosphere has a wavelength range that's perfectly transmitting, 100% transmission, then you can build a selective thermal emitter with the emissivity that sits only in that perfect transmission window, and you should be able to get 3 Kelvin. In practice, nobody's atmosphere is that good. The blue curve here is the simulated transmission spectrum of the air at Stanford University when it's quite dry. And you get about 90% of transmissivity in the wavelength range of 8 to 13 micron. Using this, if you construct a selective thermal emitter, you will get a temperature that's about 40 to 50 degrees Celsius below the ambient air temperature. And that's what we have predicted initially in the theoretical paper. And then Dr. Zhen Chen, my postdoc at the time, who is now a professor in Southeast universities in China, carried out this experiment. He take the radiative cooler, put into a vacuum chamber to cut down parasitic loss. The vacuum chamber has a zinc selenide window so that the thermal radiation can still get out. And then he sees that you can indeed get a temperature that is 40 degrees Celsius below the ambient air temperature during both daytime and nighttime. In other words, one really can get sub-ambient, sub-freezing temperature over 24 hours with this kind of radiative cooling idea if you build sufficient insulating around the radiative cooler. So I guess that gave you perhaps some sense of what one can do associated with controlling the thermal radiation. One of the questions that commonly arise is, well, it sounds like radiative cooling technology is something that you put on the roof. And of course, you put on the roof with solar cell as well. So, and it's another technology that try to benefit from a sky-facing structure. So a natural question is, how do you think about the interplay between radiative cooling and the presence of the sun? So the examples that I just showed you on radiative cooling will reflect all the sunlight, but you can actually utilize the sunlight as well. And the reason that you can do so is because the radiative cooling and the solar energy harvesting actually utilize different part of the radiation spectrum. The solar energy harvesting uses the visible part of a wavelength below 1 micron, and the radiative cooling uses the mid-infrared part at the 8 to 13 micron. So consequently, there are a lot of possibilities about the interplay of radiative cooling and the utilizing of sunlight. The most widely used, the most widely available way to use sunlight is in fact not solar cell. So if you go out of the, well, even in here, you look around and you see colors. And that color comes from the interaction of the object with the visible light. As far as the radiative cooling is concerned, certainly it would be interesting to do radiative cooling not just with a mirror structure, but with structures that has colors as well. So with that, it would be actually interesting to analyze the thermal load of a colored object. And there are a few factors that contribute to it. I mentioned radiative cooling, which is the, in the mid-infrared wavelength range, somewhere around 10 micron or so, where you can control how much heat you radiate out. In addition, when you look at the solar spectrum, there's a part that our eye cannot see that's in the near-infrared part of the solar spectrum, but nevertheless, that can control the thermal behavior of the system depending on whether that part is absorbed or not. Now, finally, on the visible part of the spectrum, there is the effect of metamerism. This is the effect concerning the fact that our eye is not a spectrometer. So for different spectrum, our eye actually can see similar colors. And different spectrum will have different power content in the solar part. So taking all these factors into account, Wei Li, who is sitting there, who was a postdoc at then and now a professor in Chinese Academy of Sciences, did this calculation where he looked at a yellow structure, so something that looked yellow. Now, but he played with all three effects, the metamerism, the visible spectrum, so two visible spectrum can give the same yellow color, the control of near-infrared solar absorption, and the radiative cooling. So if you want a cold structure, you want something that radiates very strongly in the mid-infrared. You don't want it to absorb any near-infrared solar absorption, and you play also with the visible part of absorption. And conversely, you can design a hot structure. What he showed theoretically is under the sun, the thermal load of this structure differ by about more than 800 watt per meter square. Now, to put that number into context, the entire solar energy that you have is about 1,000 watt per meter square. So this is a very large swing in terms of the thermal load. He then did an experiment where he made two different structures that are both visibly almost the same. They both look pink, and then, but they are designed based on the thermal load consideration, and then he put it under the sunlight and measured its temperature. And the remarkable result is that even though they look both almost the same, the temperature difference between them is about 40 degrees Celsius. So you can get a huge temperature swing for things with the same color. And also, the commercial paint, which has similar colors, sits somewhere in between. And this gave an indication that there is actually tremendous potential in keeping the visual appearance of something to be the same, but significantly affect the thermal properties for either heating or cooling application. So now, instead of using color, generating color with sunlight, of course, one of the technologically very important thing about the sun is the solar cell. And one thing is that things are hot under the sun, as I alluded to a few times already. So solar cell on a roof typically operates at a very high temperature because the solar heating. The typical operating temperature is about 50 to 55 degrees Celsius. And that translates into, compared with a 30 degrees Celsius operating environment, that translates into more than 1 percentage point for a silicon solar cell, which is a very substantial penalty. The solar cell certainly faces the sky, so it will be interesting to combine the solar cell technology with radiative cooling. Here is one illustration of the idea. So if you take a piece of silicon, it absorbs very strongly in the solar wavelength range, and this is how you build a solar cell in the first place. It turned out that silicon is not a very strong thermal radiator due to its chemical structure. So one thing you can do is to try to enhance the emissivity of a silicon. For example, you would like to put something on top of the silicon absorber that is visibly transparent so that the sunlight can go through. But in the infrared side, you want to enhance the emissivity so that you can radiately cool the silicon cell underneath it. And we illustrate this idea with this experiment about a solar absorber. The absorber that we use is a piece of silicon, the commonly used silicon that people use in solar cell, with an anti-reflection silicon nitride layer. Now, that's our bare absorber. Then, to do radiative cooling on this absorber, we consider two structures. One of them, we put just a thick layer of silica on top of it. And this is, as I mentioned, silica has radiative cooling characteristic. Now, the other structure that we do is we further put what we call a photonic crystal structure into silica, and this is a structure with a periodic array of air holes introduced in it. Now, this silica photonic crystal structure is visibly transparent. So here's just a demonstration of it. We put this structure on a Stanford logo, and you can still see the logo. And there's no color associated with it either. So on the solar side of the wavelength range, the three structures actually absorb very similarly. You can see this characteristic absorption of silicon that cuts off around 1 micron or so. With the photonic crystal structure, in fact, have slightly higher absorption because of a light scattering effect. On the other hand, on the thermal side, the three structures actually behave very differently. The silicon, as I mentioned, doesn't emit much. The silica flat structure have strong thermal emissivity, as indicated by the blue line here, but it has a very large dip due to reflection right in the transparency window. And the presence of photonic crystal remove this dip to give you a completely flat, near unity thermal emissivity over a fairly wide wavelength range. We now, again, do our rooftop experiment under the sun, and you can see a very large temperature difference between the bare silicon structure and also the structure with silica on top of it. The difference of this comes from the radiative cooling effect. Moreover, the photonic crystal structure that we engineer has a temperature that's consistently lower compared with silica, and that comes from the ability to enhance the thermal emissivity coming out of the structure. So what we have created here, in fact, is a visibly transparent black body emitter for cooling purposes. One would like to translate this experiment that we have done into a solar cell demonstration. This is actually a solar absorber demonstration. So with that, it would be useful to measure the solar cell spectrum. So a typical solar cell already has a glass encapsulation layer. Now, if you look at a silicon solar cell, what you see, though, is that it absorbs the visible part of the wavelengths up to 1 micron, where you can use it. But it also still absorbs significant amount of infrared light that doesn't produce photocurrent, but serve only to heat up the solar cell. So consequently, with Wei Li, we proposed this comprehensive solar cell light management strategy. We envision a coating that you can put on the solar cell that allow all the visible light to go through, but it reflects the solar spectrum that cannot be used by the silicon cell, so that it won't use those spectrum to heat up the solar cell. And finally, we design it so that it's strongly emissive in the mid-infrared wavelength range for radiated cooling. The theory indicates that if you can do this, you will get a temperature of about 6 degrees Celsius reduction when applied to standard encapsulated cell. And this translates to approximately somewhere between 0.5% to 1% percentage point of the solar cell efficiency improvement, which is quite substantial. Now, finally, in this part, there are other ways that you can combine solar energy harvesting and radiated cooling. I mentioned that you can use radiated cooling to cool down a solar cell, but you can also just do radiated cooling and solar energy harvesting separately. Again, utilize the fact that they are harvesting different part of the electromagnetic spectrum. So here is one experiment carried out by Zhen Chen, where we put a solar absorber on top of a radiated cooler. And we designed the solar absorber so that it absorbs sunlight, but are transparent in the mid-infrared wavelength range, so that the radiated cooler underneath it can still radiate the heat out through the solar absorber to the outer sky. And in the experiment, we see that under the sun, the solar absorber indeed heat up, indicating the harvesting of solar energy. In the meantime, the cooler still has temperature that's substantially below the ambient air temperature, and that shows that it is possible to simultaneously harvest solar energy and while perform radiative cooling. So that concludes this part of the talk, where I show that you can push the radiative cooling idea forward by combining that with the harvesting of solar energy. In the very last part of my talk, I'm going to get away from the sun somewhat and come back to some of the unusual use of radiated cooling during the nighttime in terms of nighttime power harvesting. So as I mentioned, there's this old idea of nighttime radiated cooling, where you take a black body emitter at night, just face the sky, you have a temperature that falls below the ambient air temperature. Now, when you have that, that naturally create a temperature gradient between the ambient and the cooler. And from your thermodynamics class, you will know that any temperature gradient can be used to generate work, to generate electricity. So based upon this, we envisioned this experiment where we take the radiated cooler and nighttime at night, have it face the sky so that it would fall below the ambient air temperature. Then on the back side, we put a thermoelectric generator that connect a heat source at the ambient temperature with the radiated cooler. Now, you have a temperature gradient here, and consequently, you ought to be able to produce electricity. So this is how the experiment looked like. The radiator cooler here is just a piece of aluminum plate painted black. So it's a very simple setup. And then on the back side of it, we put a thermoelectric cooler, and then we have it face the sky. And this actually generates electricity, and it generates enough electricity so that you can light a light-emitting diode and to see light out of it. So we thought really we are, in this case, generating light from the darkness of the night sky. In terms of potential use of this, there is a very substantial population in the world that still lack access to electricity at night. And one of the primary use of electricity at night is lighting. And this gives you a way to do direct nighttime lighting without the need for electricity storage. And also in fact, a fairly low cost and simple device setup. One can actually put this idea forward to provide 24-hour generation with a solar cell. This is an experiment that was carried out by Sid Asawararit, who is now on the faculty here in University of Sydney. So I mentioned that in the standard silicon photovoltaic cell, it had a thick layer of silica on top of it. That layer is a radiator cooler. So at night, actually, the silicon photovoltaic cell will have a temperature fall below the ambient air temperature. So in this experiment, what Sid did is he put a thermoelectric generator at the backside of a standard silicon photovoltaic cell. And so, and then he just measured the power from the photovoltaic and from the thermoelectric generator. So during the daytime, which is, let's say, around noontime here, you see power coming out of photovoltaic cell. In this case, the photovoltaic cell is hotter than ambient, so you also see a little bit of power coming out of the thermoelectric generator, so it can boost up the power a little bit. At night, the photovoltaic cell, of course, doesn't produce any power anymore, but its temperature now, because of the radiative cooling effect of silica, fall below the ambient air temperature. So consequently, the thermoelectric power generator also produces power. So in this configuration, you can actually get 24-hour power generation by augmenting a solar cell structure. The amount of power that we see in these experiments are relatively modest. As you can see here, in the silicon photovoltaic cell experiment, we have electricity generation of about 50 milliwatt per meter square. There is, in fact, practical consideration for further enhancing electric power density. And so in a theoretical paper, my student Ling Fan look at some of these considerations. For example, on the optical side, using selective emitter, on the thermal side, reducing the parasitic heat flow, and also, very importantly, control the area ratio of the radiator cooler to the area of the thermoelectric generator for better impedance matching. And she showed in the theory that there's a pathway to reach power density exceeding 1 watt per meter square. And this is a recent experiment carried out by Sid, where he took some of our vacuum setup with radiator cooler, and then really optimized the thermal emissivity spectrum of the cooler, as well as the thermal design, in particular the area ratio between the emitter and the thermoelectric generator. And he was able to demonstrate a number of electricity of 300 milliwatt per meter square. Now, in terms of harvesting energy from ambient environment in the absence of the sun, this is in fact a record number of power density that can be harvested. So these are experiments. Now, as a theorist, which myself is, one of the questions that you may ask is, well, what exactly is the theoretical limit associated with this kind of power generation in the ideal situation? So in the solar energy harvesting literature, there has been large number of work working out what is the theoretical limit for harvesting sunlight. And it turned out there's a very interesting symmetry relation that you can map every one of those schemes into a scheme that harvesting the outgoing radiation from the Earth to the outer space. And you can compute from that outgoing radiation how much work can you actually harvest. And so for every single solar energy harvesting scheme with its corresponding efficiency, there is a corresponding power density when you try to harvest from the universe of this outgoing radiation from the 300 Kelvin to 3 Kelvin. And those numbers range from about 50 watt per meter square to 150 watt per meter square, depending on the scheme. Now, the experiment that I show you, SIT experiment, has a power density that's about 2 to 3 order of magnitude below this. And as a theorist, I would say that that represents a great opportunity. It means that there's still a lot that one can do to further improve the material and the device to push this idea of harvesting outgoing radiation forward. So with that, let me briefly, here's it, that I just mentioned. With that, let me briefly summarize. I hope to give you a sense that there are a lot you can do about thermal radiation. It is a ubiquitous aspect of nature. Every one of us does it. But modern technology allows you to control it in unprecedented ways. And with that comes many interesting engineering possibilities that can have important implications for renewable energy applications. So with that, let me stop here, and thank you for your attention.